Okay, so this is a quick video about spool winding using the X winder, and we're going to wind a rope or a filament back onto a reel, and we're going to do it in such a way that there's no clumping of filament at the ends, and we can control the spacing perfectly along the length of the mandrel. Alright, so let's bring up um, a look at this is a representation of the mandrel and the filament, and here's an elemental triangle, and that's the width or the bandwidth of the filament. Here is the winding angle, and what we want to know is the distance in the circumferential direction, the length of that filament in the circumferential direction, which happens to be the bandwidth, divided by the cosine of the winding angle. So what we want to do is if we look at the end of this mandrel, what we want to do is have the first pass, so this is the width of the filament in the circumferential direction. Let's say that's the beginning of the first pass. The carriage goes down and back. We want the next filament to lay perfectly adjacent to the previous filament without having the mandrel or the carriage dwell, which would cause the filament to bunch up at the end. And then, of course, after the next down and back pass, we want the next filament to be automatically adjacent. So we're going to investigate how we're going to do this. Alternately, we could also have, say, the first pass be there, the second pass, after the carriage goes down and back, we could have a gap of one filament width. This is the filament width again in the circumferential direction, which is the bandwidth divided by the cosine of the winding angle, and then we could just continue around like this, and we'll have no bunching of the filament at the ends. So to do this, what we're going to do is take a spreadsheet. So this is the diameter. Here is the length of the mandrel. Of course, that's the circumference, and we're going to have to iterate to find a solution. So what we want to do, if the starting position on the mandrel is 0 revolutions, in this case, when the carriage goes all the way down the mandrel once, the revolutions, or the revolutions down, in this case, the mandrel will have advanced 2.53 revolutions. The carriage immediately reverses and comes back the length of the mandrel again when the mandrel then goes through 2.53 revolutions, and by the time it comes back, when the carriage returns back to the home position, it has revolved through 5.05, almost exactly, a little bit over 5 revolutions. The actual remainder is 0.05 revolutions. Okay, so that's 5% of the circumference, which is in this case a half an inch. So if the original filament width was a quarter of an inch, when you lay it on the mandrel at 59.54 degrees, and I'll show you how we're going to iterate to get that, the actual width is the circumferential width. Remember, we're going back this distance here. The circumferential width is in fact almost 0.49 inches. So if we craft a winding, and I'm going to go to the G code here in a second, at 59.54 degrees, we can exactly bring the filament back to be adjacent to the starting position plus a half an inch, which will lay the two filaments together. So this is there's also a solution at let's say 6981. I've already done this. You're going to have to at 6981 we're going to go 8 revolutions. So there is a solution to this problem at 69.81 degrees. Again, you can just what you want to do is sort of go through these winding angles until the gap spacing, which is the amount that the mandrel has advanced past the original position, is equal to or almost nearly equal to the filament width in the circumferential direction. So, and we're here, this is a little bit over 8 revolutions. If we wanted to go the other spacing which I mentioned, so that's 6998, let's try that, 6998. What we get is a spacing of twice the original, or the bandwidth divided by the cosine. So in that case we have we'll lay filament, as I showed in this particular case, where the filament will lay a gap of 1 filament width without, remember, the whole purpose being that the mandrel does not dwell at the end. So let's bring up the designer, and I've input all of the information here. We're at 59.54, so let's go back to the 59.54. This will be directly adjacent. We're not having a gap here. I'm going to bring up the designer, 59.54. We're doing 2 layers. Here's the width of 3 inches. We've got a 14-inch length of the mandrel. We're running this just slow for the moment. If we look at the G-code here, now here is the G-code that's output from the file, which is right here. So this is all setup information, as you've probably seen this before. And what we want to do is, here is the beginning of the first layer. So what we want to do is, here is the mandrel is started at 14.9 RPM. We're marking the starting spot. The carriage is now advancing at 1.38 inches per second down to a z coordinate of 24. Remember, there's the 24. We're advancing down to 24. And at this point, we do not want to go through a full revolution, so I'm going to take that out. We'll go ahead and mark the end position, and we're going to come back at 1.38 inches a second back to a z coordinate of 10. This is going to add a full revolution. We do not want that. And then this command is going, we already know the position of the mandrel when this returns, remember, because we've already calculated that, so we don't want the mandrel to dwell whatsoever. So I'm going to just totally remove that. Now let's go to the second pass. We go back down to 24. We dwell. We're not going to dwell here either at the far end, because we already know, we've calculated this condition a priori, so we're going to get rid of that dwell, and we're going to get rid of that dwell. So all I'm going to do is just basically go through and get rid of all these dwell commands. Alright, let me do that, hold on. Okay, so I've gone through and removed all of that. So this is what the G-code file looks like. On the first pass, I'm not dwelling anywhere. In fact, I don't even need to mark these angle conditions, because I'm not, there's no position of the mandrel relative to the marking position, so I don't even need them anyway. So here's the end. Let's count how many passes. We've got 1. This is 1 pass down and back. 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have made 20 passes down and back. So what's 20? 20, basically, remember, we have 20 times 0.5, which is about 10. It's just 10 inches in circumference, and that in fact is the circumference of the entire, so we have covered the full surface area of the mandrel at this point. We have not dwelled anywhere. So at this point, after the first pass, the mandrel surface is now fully covered. The carriage has never dwelled at the end of the pass. And what we're going to do before we start the second layer is we are now in fact going to institute a dwell, and this will advance the mandrel through 9 degrees. That way we're going to offset the next layer. We're going to shift it by a half of filament width. And then we're going to continue, and again I'm going to go remove all of this, and I'm going to do that in just a second. Okay, so I removed now all of the dwell commands from the second layer. There's 20 passes down and back. We will then have stacked up another surface layer on top of the first layer. Remember, it was offset by 9 degrees, and we can continue to keep repeating this pattern. So if I come down here and I copy all of this, I'm going to then do a cut and paste. I'll drop it there, and we'll just keep going all the way down again. And just keep adding layers and layers until we've got enough, until we're satisfied with that. So that's basically the drill. To be able to spool wind using the X-winder without the carriage dwelling and without the filament mounding up at either end. And remember, the key here is that you need to get the mandrel, when the carriage returns after a full pass, to be just slightly over an integer number of revolutions, and in fact just enough so that that gap is equal to the bandwidth of the filament divided by the cosine of the winding angle, and you need to sort of go through and find a solution. So there are only a handful of solutions of winding angles that will give you this exact condition. In any event, that's basically the content of the video.